On the screen, a single line appears for a breath. This title is used as a narrative device. This film examines the U.S. factory whose engines made sustained strikes on Japan possible. The line holds, then fades, and the camera drops into a room where the air itself seems to burn. At 2:37 a.m., the forge glows like a captured sun. Molten metal rivers flow in silence that isn't silence. A low mechanical hum, the breath of furnaces, the distant clank of a hammer. Sparks drift like bright ash and gather on the shoulders of men and women moving with rehearsed urgency. A torch hisses. Someone curses under his breath. A spotlight picks out a scored notebook on a stool. Pages thick with calculations, margins crowded with circles and arrows. "It's splitting again," a voice says, flat, exhausted, unshaken. The voice belongs to Frederick Brackett, chief metallurgist, and in it is the weary insistence of someone who has seen more metal fail than succeed. He says the words, and the room reacts as if to a physical blow. Heads turn. The foreman half stops. A young mechanic named Samuel Ortiz fingers a wrench and looks at the cracked piston like a man staring at a loved one's wound. This is how the problem announces itself. Not with a memo, not in a lecture, but in repeated fracture. Pistons that sheared at the base, crankcases gashed by thermal stress, test rigs that detonated in a spray of aluminum shards and nightmare blue flames. The order from the Air Forces arrived in a different language, numbers and demands that read like a dare. Build an engine that can lift a bomber heavy with fuel and payload, climb higher, run hotter, and run longer than anything that came before. Give a four-engine bomber the power to cross oceans and loiter at altitude where enemy fighters had trouble reaching. The Pacific was a geography as severe as any enemy. Distance multiplied every problem. The task was not only engineering, it was a contest with physics. Outside the plant in East Hartford, Connecticut, the night was winter raw. Inside the Pratt & Whitney facility, hours later than most a man should be allowed to work, they kept stoking the fire. The engine at the center of this exacting obsession would be called the R-4360 Wasp Major, the largest radial aircraft engine mass-produced in the piston era. To the men and women on the floor, it was simply the project. To the generals in Washington, it was a possible answer to a tactical problem. Get more payload to farther targets, higher and longer. Maps, schematic overlays, and official memos matter to the story, and they will be shown. But first, the human rhythm. A nervous laugh cracks at the end of a shift. A test stand operator, Robert Kane, checks a gauge for the third time and doesn't notice the bead of oil on his glove until it sparks. He will be injured days later when a containment fails during an endurance run, a line scratched in a hospital log and in his crew's memory. Ortiz, only 22 that winter, learns to read the sheet metal language of a crankcase with a fingertip. "You can tell where it wants to break," he would later say, half to himself, half to anyone who would listen. "The metal tells you." What they were learning, at first, was how not to make the engine. There is a peculiar pedagogy in failure. A bolt torques and loosens the wrong way. A cooling duct sits one thread off-center and a cylinder overheats. A vibration at 1700 RPM hums through a crankcase and fine hairline fractures begin their slow and visible work. Tests were built to be predictable, and they were not. Rigs were designed for endurance, and they exploded. The plant became, for months and years, a laboratory of failure. Whiteboards of attempted fixes, scrap piles of prototypes, scribbled hypotheses pinned to lockers. The engine designers faced a compounding list of contradictions. Radial engines had always struggled with heat in the rear cylinders. Now the challenge was multiplied by size. The R4360 would have more cylinders arranged in rows, and as the diameter grew, the cooling of inner rows became a problem of diminishing returns. Increasing power required stronger materials, but stronger at high temperature often meant brittle at stress. Bolting down more metal increased weight. Weight cut endurance. Supercharging could feed more air and thus more fuel into the cylinders, but that intensifies temperatures and stresses beyond anything existing combustion chambers had seen. Frederick Brackett's corner of the plant smelled different from the lines where women riveted cows. It smelled of flux and hot alloy and something that combined sweat and a chemical tang. The smell of minds working on problems that alter the tools of war. Brackett did not imagine the political consequences when he measured tiny microstructures in a metallograph. He saw the problem as a metal man would: grain boundaries, precipitates, and inclusions, imperfections that could become the seed of catastrophe under cyclical load. He took pride that his language stayed close to the laboratory. "If the grain will grow through, it will fail," he would write in a margin. The men who read him learned to translate the lab into the field. If the metal cracks here, the bomber cannot bring home men who've flown many missions. Not all innovations were confined to the chemistry bench. Harold Wentworth, a draftsman whose name appears in a handful of memos and a single photograph, sketched an idea on the back of an envelope: an impeller cooling fan that could force more air into the nooks of a multi-row radio. Its silhouette was humble, curved blades, a narrow hub, yet it solved a problem that no alloy alone could fix. The fan would not make the engine safe by itself, but it changed the conversation from how to survive heat to how to carry heat away fast enough to survive. The plant floor is full of such small acts of invention. They never arrive as monolithic breakthroughs, but as stubborn additions, an extra duct here, a baffle there, that change the variables of a stubborn equation. The test cell is where promise and peril have their most public argument. Imagine a cavernous room built to hold the sound of a hurricane. Thick concrete, immense steel beams, an observation gallery shielded behind glass. A 4-engine R43060 prototype mounts a stand. Technicians fasten wires, heart rates spike in measured beats. The engine starts, and for the first minute, everything is ceremonial. Valves open, oil pressure climbs, instruments settle. Then, the frequencies that hide within motion begin to reveal themselves, resonances that engineers had predicted in blue ink but had not felt in the bones. Bearings heat unevenly. Vibration monitors trace a jagged, beautiful waveform on a paper scroll. 3 minutes after startup, the room goes quiet in a different way. Everyone is listening, and then the test cell coughs. A rod snaps, a containment seal fails, and the sound is a splintered clap that throws men back from the observation window. There are, after the test, the scavenged pieces of intelligence. A congealed smear of alloy on a bolt, a smear of oil and soot like a painting, a shard small enough to hide in a palm that will tell metallurgists everything about the load it saw. They file those fragments like relics. They photograph them. They seal them. Kine, who had been the one to check the gauge that morning, will spend weeks in recovery and months after that telling anyone who will listen how the instruments were right and the margins weren't enough. "You don't get to trust a new engine," he said later, the scar over his knuckle white even in old photographs. A quiet cultural choreography develops in the plant. Women operate jigs and rivet guns with an economy of motion borrowed from past weeks of repetition. Men lift and line up cases, big as trunks, moving on padded rollers like funeral pallbearers for steel. At the X-ray inspection booths, shadows of hidden flaws appear on film like ghostly continents, veins of impurity, trapped slag, voids where metal refused to flow. These booths are lit like confessionals, and technicians learn to read them with the seriousness of priests. The Air Forces did not ask for glory. They asked for numbers: more horsepower, less weight, greater reliability. General Hap Arnold's office does not appear in the factory's daily life, but its requirements set the tempo. The laboratory became a relay point in a supply chain that would wind through multiple states. Mills that could draw the rare alloys, tool makers who could machine the crankshafts, propeller manufacturers who could temper blades to resist the proposition of thrust from 10,000 horses. The plant could not act alone. 100 small companies, some of them run from garages or small-town main streets, were suddenly critical links. The nation shifted production in ways invisible if you lived only in one town and terrifying if you worked the machines. The story of the R43060 is as much a story of networks as it is of metals and shafts. The early months of testing were a sequence of humiliations that taught a template: test, fail, analyze, redesign, and try again. The pace burned people down. Sleep became a luxury equated with risk, since the next shift could catch up with an unresolved design defect. Some nights, engineers argued until dawn over whether to harden a shaft or to redesign the lubrication path entirely. They drafted mock-ups and held them up to the light with the reverence of sculptors. "We were like men shaving a statue in the dark," an engineer later admitted, working by feel, hoping not to take off too much. Between the discrete mechanical failures lurked problems of metallurgy that required years of concentrated thought to solve. Aluminum and its alloys promise lightness. Their Achilles heel is high temperature strength. At high temperatures, some alloys creep, slowly deforming under constant stress, while others form microscopic voids that become catastrophic cracks under cyclic loading. Brackett began to think in microseconds and in grain boundary lines, in how additives like copper and silicon shift the performance envelope. He championed experiments with new heat treatments, quenching protocols that reconfigured grain structures, annealing practices that allowed the metal to relax internal stresses without losing tensile strength. Every oven cycle, every tempering run was a small attempt to outrun failure. Material solutions alone did not answer the problem of vibration. An engine that produced tremendous torque could still sing itself apart if the harmonics of its rotating masses matched the natural vibration modes of its cases and mounts. Engineers drew diagrams of standing waves and compared them to the sound the engine made when idling. They balanced masses meticulously, sometimes shaving grams from counterweights and occasionally redesigning the crankshafts into subtly different geometries. They borrowed language from music, nodes, antinodes, resonant frequencies, and replaced metaphor with metal. "If you can quiet the melody," one machinist wrote on a scrap, "the song will stop tearing the house down." As iterations multiplied, so did production questions. An idea that succeeded in the shop must be repeatable on a line. The plant's foreman learned that what makes a prototype brilliant can make a fleet fragile if the new process is too touchy. To mass-produce the R43060 demanded new tooling. Massive jigs to hold the cases perfectly, presses that could cold-form cowlings to tolerances tighter than 1/100th of an inch, and a quality control regimen that included X-ray inspection for internal voids and 4-hour acceptance runs for each completed engine. Each engine would be turned up on a bench and run for a prescribed period at specified RPMs, watched by technicians using all the senses: sight for leaks, ears for odd harmonics, fingers for heat. Scale brought human choreography to a level few had seen outside of major shipyards. Women streamed onto assembly stations, their palms stained with oil, hair tucked under kerchiefs. They drilled and riveted, and, in the way of repetitive labor, found a rhythm that let the mind wander to letters from home or to ration coupons and bus schedules. Men who had been tool makers for decades found themselves learning to work in assembly teams with the efficiency of conveyor belts. The massed sound of rivet guns became a constant percussion, the industrial equivalent of a heartbeat moving the plant forward. And then there were the test flights. No matter how promising a bench run looked, an engine in the air is a different animal. The first B-20 lines carrying prototypes of the R-4360 prepared on a runway that was itself a theater of quiet terror. Pilots' reports are practical things: pressure readings, temperature graphs, and an almost superstitious note about how the aircraft felt. Eddie Allen, a pilot who flew early trials, would later speak in short, clipped lines about the first time the plane climbed on the new engines. The climb rate surprised him. The rumble was deeper, and the airframe seemed to breathe differently. Flight engineers like Lieutenant Jack Simmons kept logbooks with neat columns. When the Wasp Major picked up speed, the entries read like someone marking off minutes lived in a new world. These triumphs carried moral weight that the floor of the plant could not ignore. Workers learned that their engine, when fitted to bombers and sent across the Pacific, altered how war could be waged. It enabled flights longer than any before and ceilings that put crews beyond easy interception. That knowledge was a hard thing to carry. A riveter who had spent months fitting cowls learned in a newspaper column that her work had been part of missions that resulted in citywide conflagrations overseas. She was proud of the craft, but fraught with unease. The juxtaposition is a recurrent note in everyone's recollection of those years. They measured their pride in the product against the moral ledger that was never simple. One afternoon, after a particularly rough week of failures, Brackett walked through the plant floor and stopped at the line where propellers waited. Hamilton Standard had been a partner, and those propellers were not merely blades, but arcs of potential energy. A propeller the size required by the B-29 and the R-4360 had to be enormous, bent and tempered to handle the torque, balanced down to a fraction of an ounce. Propellers, Brackett knew, are the last translators of engine to air. If they failed, everything else would mean little. He ran his gloved hand along a polished hub and then looked back toward the furnaces. These triumphs carried moral weight that the floor of the plant could not ignore. Workers learned that their engine, when fitted to bombers and sent across the Pacific, altered how war could be waged. It enabled flights longer than any before, and ceilings that put crews beyond easy interception. That knowledge was a hard thing to carry. A riveter who had spent months fitting cowls learned in a newspaper column that her work had been part of missions that resulted in citywide conflagrations overseas. She was proud of the craft, but fraught with unease. The juxtaposition is a recurrent note in everyone's recollection of those years. They measured their pride in the product against the moral ledger that was never simple. One afternoon, after a particularly rough week of failures, Brackett walked through the plant floor and stopped at the line where propellers waited. Hamilton Standard had been a partner, and those propellers were not merely blades, but arcs of potential energy. A propeller the size required by the B-29 and the R-4360 had to be enormous, bent and tempered to handle the torque, balanced down to a fraction of an ounce. Propellers, Brackett knew, are the last translators of engine to air. If they failed, everything else would mean little. He ran his gloved hand along a polished hub and then looked back toward the furnaces.
The decision was always partly metallurgical and partly moral. How much power did you give someone, and at what cost? Behind closed doors, administrators fretted over supply chains and deadlines. Contracts had been signed with the urgency of war. Deadlines were not business targets, but delivery windows that might mean the difference between a successful campaign and one that bled time. The factory responded with improvisations. Toolmakers repaired presses at 2 in the morning. Airline engineers redesigned part numbering systems to track individual specimens. The plant's logbooks filled with notes. Repaired jig number 7. Ordered extra cam bushings. Hold for final inspection. Every small delay could cascade. Every small innovation could accelerate a line. Yet the plant's greatest teacher was its test bed. The pattern of learning revealed itself in neat cycles. Each failure suggested a variable to change: material composition, oil passage geometry, baffle shape, heat treatment schedule. Teams ran what they called root cause investigations. They traced back from a broken crankshaft to the mill that rolled the metal, to the bar stock that arrived with microscopic slag, to the supplier's furnace work. The audit trail became a map of interdependence. Brackett's labs logged everything. They measured tensile strength after every new heat treatment. They photographed fracture surfaces and set them beside old ones, looking for the faint fingerprints of improvement. There were small human crises along the way. Kane's injury silenced an entire row for a week. Ortiz fainted once from exhaustion in a shipping bay and woke to shouts and a half-dozen faces. Yet the project had a momentum of its own and an authority that required, almost ritualistically, that every instrument be rechecked and every assumption challenged. Hunches had to be tested, not merely talked about. A young draftsman proposing a fan blade had to build a model and prove its effect in a wind tunnel before a foreman would greenlight its incorporation. By the time the first R4360 prototype completed an extended endurance run without catastrophic failure, it was less a single moment of revelation than the sum of thousands of marginal gains. A baffle here, a quench cycle there, an extra oil gallery. Each small change shifted the probability of survival. The test report was cautious. Significant improvement observed, it read. And the team celebrated in the only way they had learned to celebrate, piecemeal, with shared cigarettes and a quiet nod toward the nights they had lost. After that first cautious success, the plant's tempo changed. Success breeds pressure, and pressure sharpens focus, but also raises stakes. The earlier failures remained etched in memory. The specter of a fragility revealed in the past made every new engine a candidate for an audit by ghosts.
They ramped up production, and with production came the need to ensure that what they produced on Monday matched the prototype of the lab bench. The X-ray booths multiplied, acceptance runs multiplied. Women drilled with steadiness like that of a metronome. Men who had once been solitary craftsmen now had to make identical copies of those rarefied items that had, in the hands of a few, changed the map of practical possibility. And yet, for all the machinery and calculation, the plant's beating heart remained human. There were moments of small tenderness that no schematic could account for. A foreman bringing soup to a sick machinist. A young woman in the riveting line folding a scrap of a newspaper into a neat square and sliding it into a pocket for good luck. A draftsman who carefully wrote for Sam on a drawing and left it on a bench. These gestures were not ephemera. They were the fabric that held the technical work together. This is where the first part of the story pauses, not at an end, but at a hinge. The plant had proven that it could learn from failure, that small engineering acts could accumulate into survivable systems, and that the human network surrounding machines could scale to the demands of mass production. They had seen the engine run in flight, and they had begun to accept the moral complexity of what their labor enabled. The next steps would push them further, against materials that still refused to conform, against vibration modes that hid in the mid-range, and into production volumes that would test the limits of quality control. They would face decisions about which compromises were acceptable and which would court disaster. In a quiet hallway, Brackett paused by a window and looked out where the runway met gray sky. He folded his hands the way a man folds them when he is trying to measure his own fatigue. "We have to make it hold," he told a colleague, and the sentence was less a technical brief than a vow. The plant listened as if to a prayer. If this story is holding your attention, consider subscribing for more deep dives into the machines and the people who made them. There is more to come about the breakthroughs that turned tentative runs into operational power, and about the human cost that followed those breakthroughs. And so they returned to the lab, Brackett to micrographs, Ortiz to the line, Kane to convalescence and the careful retelling of what went wrong. The next experiment would be a redesign of the cooling path. The next test, a longer endurance run. The next production decision, one that would echo far beyond the plant gates. For now, the furnaces glowed, and the watch continued. They returned to the lab with the exhausted satisfaction of men who had survived another round of examination and come back to speak of it. The next months were a rhythm of small revolutions, each one a tiny redefinition of possibility.
In the white light of the metallograph room, Brackett traced patterns that looked like river deltas and decided which tributaries to redirect. At a bench down the aisle, Harold Wentworth's fan model acquired real blades, carved from the same steel that had come to mean both salvation and danger. Ortiz tightened bolts with a deliberateness born of the weeks when a single misthread had meant a test stand's explosion. You can describe these changes in bullet points, quench here, baffle there, but the plant understood them through touch and taste. An oven cycle changed color in a way someone could see in a strip of sample. A shaft's surface finished to a luster that told the machinist it would take a torque without giving. The fans were tested in a tunnel that smelled like cut metal and dust. When the smallest models proved effective in redirecting airflow over the inner rows of cylinders, designers scaled the blades up, adapted hubs, and adjusted the baffle geometry so the added air did not disturb oil flow or create new vortices that might, in their turn, become enemies. Explaining the impeller fan without watching it is like describing the way a bell sounds. You can say it rings, but the nuance of tone must be heard. Imagine the multi-row radial as an orchestra where some instruments are buried behind others. The fan was a trombone that pushed air past the front ranks to the back ones, keeping temperatures closer and preventing the inner cylinders from becoming ovens. It did not solve every problem. Metallurgy and lubrication still required their exacting attention, but it took a variable that had been stubborn and made it malleable. Wentworth's modest sketch, once turned into steel and balanced with the care of a watchmaker, reduced peak cylinder head temperatures in a way that let designers trade off some material strength for weight and acceptability. Metallurgy and heat treatment continued to be Brackett's domain. He and his technicians treated bars of alloy like living things, subjecting them to sequences of heat and shock that rearranged atoms into more favorable alignments. They experimented with solution treatments followed by aging cycles, meant to precipitate tiny, hard particles within the aluminum matrix, particles that would hold shape at higher temperatures. If the idea sounds arcane, think instead of tempering a blade so that the edge will hold. The principle is identical, but applied to a massive crankcase that must survive repeated, sometimes violent, cycles of combustion. One breakthrough was not dramatic, it was patient. The lab found a schedule of heat treatment that allowed the alloy to resist creep, a slow, inexorable deformation at elevated temperature, and at the same time to avoid embrittlement. They achieved this not by a single stroke of genius, but by an accumulation of run charts, a pile of failed specimens, and a handful of acceptance runs that slowly edged up the probability that a part would survive a 1,000-hour run. One breakthrough was not dramatic, it was patient. The lab found a schedule of heat treatment that allowed the alloy to resist creep, a slow, inexorable deformation at elevated temperature, and at the same time to avoid embrittlement. They achieved this not by a single stroke of genius, but by an accumulation of run charts, a pile of failed specimens, and a handful of acceptance runs that slowly edged up the probability that a part would survive a 1,000-hour run.
They learned to read the fingerprints left on fracture surfaces, the micro-tearing, the dimples where ductile failure had occurred, and to correlate those features back to specific furnace temperatures and cooling rates. It was forensic work, and Brackett enjoyed it with a grim satisfaction. The metal told a story. He only had to learn to read it. Another axis of progress was the forced induction system, the multi-stage supercharger that would feed the engine more oxygen when the aircraft climbed toward thinner air. The principle was simple on paper. Compress air in stages, cool it between stages if possible, and finally cram as much as safely possible into the cylinders so more fuel could be burned. Doing it for an engine of this scale, however, was like scaling up a drawing. Tolerances tighten, heat increases, and every duct and bearing becomes a potential point of failure. Engineers designed a 3-stage supercharger to keep manifold pressures usable at high altitude. They added intercoolers where weight allowed and redesigned bearings to handle the increased loads and rotational speeds. It was a delicate choreography. Add too much boost, and a head gasket or a piston ring would be sacrificed. Add too little, and the promise of increased payload vanished. Vibration control also evolved into a craft in its own right. The team learned to think of rotating assemblies as living, vibrating things with personalities. Dampers and harmonic absorbers were placed where a spectral analysis showed dangerous peaks. Masses were moved by fractions of an ounce in counterweights. When a crankshaft could not be tamed by balancing alone, its geometry was altered. The curve of the fillet at a rod journal changed subtly, and suddenly a resonant peak moved out of the operating window. The language of the shop became half engineering and half poetry. Nodes and antinodes, the engine's breath, the way a case sang. That singing had nearly been fatal in early tests. They learned to quiet it. While design refinements moved forward in labs and workshops, the shop floor adapted innovations for repeatability. Toolmakers translated prototype fits into jigs that could clamp thousands of parts in the same relation. Inspection protocols were formalized. Sampling plans became a science. A certain percentage of crankshafts would be micromagnetically inspected for subsurface faults. Every crankcase went under an X-ray, and assemblies would be run for acceptance periods long enough to surface creeping failures. The X-ray booths, once rare, became a ritual checkpoint. Technicians there learned to read the ghostly maps on film, to identify the slight needle point of an inclusion or the faint seam where 2 pores of metal had failed to integrate. Scale brought its own surprises. A tweak that worked well with hand fitting sometimes failed spectacularly when seen through the lens of production variability. Tolerances that were tolerable with a skilled fitter became unacceptable when several hundred pieces were produced daily. The foreman responded with training programs, revised assembly drawings, and the creation of specialized work cells where tasks were repeated and optimized. They developed checklists that read like prayers, torque values, sequence of tightening, lubrication points, because the right sequence could be the difference between an engine that passed its acceptance run and one that did not. The human cost of speed and scale did not disappear. Robert Kane returned to the plant with a scar and a gentleness that made his colleagues careful around him. He developed a fastidiousness in test setup that bordered on ritual. His glove checks, his tape recording of the sequence of valves, his insistence that no instrument be trusted without redundancy. Ortiz, hardened by tasks and by an early fainting episode, took on mentorship of younger men on the line. He learned to read the subtle cues in a case's casting marks that hinted at trapped gas pockets. Brackett remained the architect of material science, but he also became the confessor to machinists who needed to know whether to rerun a heat treatment or risk saving time. When the engines began to pass longer and longer endurance runs, hours at higher RPMs, tempering the confidence of pilots and engineers alike, a new set of people entered the story. The ground crews and flight engineers whose job it was to translate bench success into reliability in the field. They invented logbook practices that would become sacred. Consistent oil sampling, scheduled compression checks, and pre-flight checklists that included specific temperature and pressure curves. These practices reduced in-flight failures by catching early signs of wear and imbalance. Pilots noticed. Lieutenant Jack Simmons recorded in careful columns the tempering of the aircraft's personality as new engines replaced older ones. Smoother climb, fewer mid-level fires, better throttle response.
Flight tests became stages where the engine's story met the unpredictable theater of weather, aerodynamics, and human perception. Early in a trial, Eddie Allen recalled how the aircraft's response on climb felt less like a machine and more like a living thing, a phrase that amused engineers but captured something essential. Engines in the air had to be predictable in ways bench runs could not guarantee. Pilots reported how torque translated to control forces, how manifold pressure changes altered how they trimmed the aircraft, and how engine failures were not just mechanical problems but exercises in crew coordination. Pilots and crews practiced failure drills obsessively, and those rehearsals saved lives when, in later missions, engines would go out of service. As the engines matured, they began to influence strategy.
Not in the sense of determining policy without human agency. The generals, politicians, and commanders still did that work, but by changing the set of options available. Aircraft with the new engines could carry heavier loads farther and maintain service ceilings that had been previously out of reach. That expansion of capability altered planners' calculus. Routes that had required intermediate staging were reimagined as continuous. The ethical dimension of that capability unfolded in tandem with the technical one. Men and women who had spent years improving combustion chambers read newspapers describing the effects of missions that harnessed those capabilities. The plant's crush of achievement came with a ledger of consequence. Workers reacted in complicated ways. Some felt a moral equivocation, a pride in craftsmanship undercut by unease about how that craft was employed. An assemblywoman who had once refused to discuss her work at dinner now found herself grappling with reports of entire districts burned. Others, including families who had lost sons in combat, saw their labor as a direct contribution to winning a war, to shortening conflict, and to preserving surviving kin. These contradictions were never fully resolved. Brackett, who had always spoken in the language of metal, sometimes allowed himself a private note of conscience. He would run a fingertip along a cracked piston kept in a glass case and feel the history of decisions pressed into its surface. That piston, small, scarred, and ordinary seeming, became in later years a kind of talisman. When the fighting stopped and museums began cataloging artifacts, curators found that objects like Brackett's piston carried stories that the big machines could not. The uncertainty of a heat treatment, the exact sequence of a failed test, the name of a man who had refused to accept impossible. The piston stood for fragility and resilience simultaneously. How even the most carefully forged metal can give way, and how persistence in the laboratory can alter the arc of war technology. Production continued to rise. The plant transitioned from prototype to produce at a tempo that required not just more hands, but better processes. The tool rooms expanded, and the supply chain knitting together mills, machine shops, propeller plants, and test cells had to be tighter than ever. Shipping schedules, maintenance windows, and part serialization became critical. Innovations in stamping and cold forming made cowlings faster to produce. Tempering ovens with better control meant more consistent alloy properties, and new non-destructive testing methods reduced field failures. The scale-up also produced its own moral and safety innovations. Work hour rules, medical screening, and early versions of what we would now call ergonomics were introduced incrementally to reduce fatigue-related errors. Managers learned, often painfully, that pushing men past a certain limit produced more defects than it solved. That practical learning, how to preserve human capital while increasing output, was as important as any technical prescription. Meanwhile, the propellers that translated the engine's torque into thrust required attention of their own. Their blades had to be shaped, tempered, and balanced to resist enormous aerodynamic loads. Hamilton Standard became a partner in this endeavor, supplying propeller assemblies tested to withstand the torsional impulses of the R4360 at high RPMs.
Propeller failure had always been catastrophic, so the joint teams worked on materials and on variable pitch mechanisms that allowed blades to change their angle for maximum efficiency at different speeds and altitudes. That sophistication, married to the engine's power, produced the dramatic takeoffs and long climbs that pilots would later describe in clipped, reverent reports. As production matured and aircraft carrying the new engines entered squadrons, the operational tempo increased. Maintenance depots learned to service the larger, heavier components, and an industrial ballet unfolded across airfields. Technicians swapped power plants between missions. Mechanics performed compression and valve checks under time pressure. And logistics officers ensured spare parts moved where they were needed most. The engine's success depended not just on the people who forged and fitted its components, but on an entire ecosystem of support. By the late stages of wartime production, the plant had become an orchestra of assignable roles: metallurgists, machinists, toolmakers, testers, drillers, inspectors, all coordinated with an efficiency that belied the chaos of early experiments. Yet for all its ordered motion, the plant remained a place of improvisation. When a supplier's furnace went down, engineers looked for materials in unexpected places. When a press failed, toolmakers rewired jigs and borrowed presses from adjacent plants. That improvisation, a cultural trait as much as an operational one, kept the lines moving. The personal arcs of the named figures carried through this engine's final trials. Kane, with his scar and patience, became a champion of redundancy in test setups. He insisted that the instrument panels have multiple sensors in case one gave false assurance. Ortiz, who had once learned to read castings with his fingertips, became a trainer. His experience transferred into checklists and shorthand instructions. Brackett continued to push the lab envelope, but he also began to spend more time in the plant extracting process improvements from workers who had once seemed merely hands on the line. Wentworth's fan found its place in production, and he resigned himself to a job of refinement, changing blade counts, hub shapes, and inlet geometries, not for glory, but for reliability. The engine's operational impact across the Pacific cannot be reduced to a single line of consequences, and the script refuses to do so.
It is accurate to say that extended range and higher ceilings broaden strategic options. It is similarly accurate to insist that decisions about targets, methods of attack, and political goals were not made by engines. Those decisions were human and often excruciating. What the factory built, what Brackett, Ortiz, Kane, Wentworth, the riveters, the toolmakers, and the pilots combined to produce was an enabler, a technology that allowed certain missions to be conceived and executed in ways that would not have been possible otherwise. Faced with that duality, pride and industrial achievement, and the moral implications of its application, many workers processed the ambivalence in private and in public. Some sought solace in the belief that their labor defended their country and protected loved ones. Others turned to community and quiet acts of memorial, placing photos and small mementos in the lockers of those who did not return. The factories, like the airfields, kept lists of names. Their walls accumulated plaques and letters. In the quieter post-war years, reunions and veterans gatherings became places for conversations that sometimes resolved nothing but made the weight of memory lighter to carry. When hostilities ended and the world began the difficult work of reconstruction, the plant's role shifted. The R-4360 did not vanish overnight. Its scale and reliability had made it suitable for large aircraft that would serve in transport, reconnaissance, and in limited commercial roles for a brief period. But the march of technology was relentless. Turbines and jets, with their different sets of trade-offs, were already on the horizon. The skill sets developed in the R-4360 program, metallurgy, precision machining, non-destructive testing, and systems thinking, migrated into new industries. Engineers who had learned to manage heat and vibration found their expertise applicable to turbines. Toolmakers who had developed novel jigs helped build early jet engine components.
Test cell operators adapted to new forms of measurement. Brackett's laboratory notes, filed in meticulous stacks, later informed research into high-temperature alloys and treatment schedules that would be relevant in turbine metallurgy. The language of grain structure and precipitate control translated into the vocabulary of jet engine design. Harold Wentworth's impeller concept, applied to cooling, found echoes in turbine blade cooling strategies, albeit in a radically different thermodynamic context. The human capital, more than any single artifact, was the plant's post-war gift to aerospace progress. The R-4360s themselves found second lives in transports and in record-setting aircraft that celebrated the end of one era and the emergence of another. Museums eventually acquired surviving engines, and the visceral experience of standing beside a Wasp Major, its diameter, the curvature of its cowlings, the weight of the propeller hub, conveyed something that photographs could not: the physicality of a technology that had once been near impossible to realize. Curators learned to display not just the engine, but the network behind it: photographs of assembly lines, oral histories, and artifacts that told the human part of the story. In those museums, Brackett's cracked piston found a place on a shelf with a small printed note explaining its provenance. Visitors would come and stand, some in silence, some with cameras, and read the plaque. For a young engineer peering through a preserved X-ray booth or a tooth-mark sketch of a failed crankshaft, the piston was more than metal. It was a lesson. It said, even the most formidable challenges can be solved only incrementally. Durability is negotiated in the margins. Human hands and stubbornness mattered. A final visit to the plant in the years after the war reveals a site gradually repurposed. Parts of the facility were converted to peacetime manufacturing. Some halls were mothballed, and others were adapted for new technologies. But the architecture of problem-solving, the way a bench sat next to an oven, the adjacency of design to production, persisted. Managers who had learned to run an enormous, complex program applied those organizational lessons to civilian projects. Communities that had become economically tied to the plant pivoted, drawing on their pool of experienced technicians and machinists. Brackett lived long enough to see his work recognized in technical papers and in conversations among metallurgists. He never became a public celebrity. His satisfaction was private and edged with something like exhaustion. He would, on occasion, be asked about the moral weight of the machines he had helped enable. He would reply, as he had once written in a margin of a lab notebook, that the lab's obligation was to truth in material behavior, and that how societies chose to use that truth was beyond the remit of heat treatment tables. It is an answer that satisfies logically, but not always emotionally. Those who had worked side by side with him knew that his constancy included a kind of ethical awareness. The decision to make something hold was both technical and moral. The post-war stories that leak into public memory tend to crystallize into tidy arcs: invention, victory, peace. The reality is messier. The engine did what engineers designed it to. It produced power reliably enough to expand operational options. What followed, the strategic choices, the suffering, the political consequences, were human, complex, and irreversible in ways no machine can fully anticipate. In a plant in East Hartford, the people who crafted combustion chambers and balanced counterweights carried that complexity with them. They told their grandchildren how they worked, what they lost, what they endured. Some told batched stories filled with pride. Others told accounts shaded with sorrow. In the quiet of a museum evening, when a Wasp Major sits under soft lights and the footfall of visitors thins, the engine seems almost to breathe at a human pace. You can stand there and imagine the hot, noisy days when it was a promise, a problem, and then a tool of power. You can see Brackett's fingerprints in the artifacts and the logic of a fan blade solved with a draftsman's pencil. You can see Ortiz's apprenticeship transformed into mentorship, Kane's scar reframed as a cautionary badge that improved test procedures, and Wentworth's envelope sketch turned into a production part. Those human traces are the through line of the story, what makes the R4360 less a mechanical monolith and more a distributed network of choices, failures, and small triumphs. Technology, in this recounting, is not separate from the people who shape it. It is an outcome of their labor, their compromises, and their values. The engine that roared on East Hartford runways carried in its alloy and geometry the signatures of people who'd learned to endure and to refine. The moral ledger remains unsettled. The same machines that enabled long-range sorties also helped shape a wartime geography in which cities became targets and populations suffered. The factory bore witness to that dissonance. Workers read dispatches and looked at their hands. They knew the double edge of their craft. A generation of engineers and technicians learned technical truths and ethical ones, sometimes in the same breath. That power demands responsibility. That precision can have consequences far beyond the shop floor. And that memory is a necessary companion to invention. In the end, the plant's story folds into a wider American industrial story. A nation that mobilized resources, talent, and courage to solve problems that at first seemed insurmountable, and that did so with both brilliance and cost. The R4360 remained for a time a crowning technical achievement in piston engine design. Its lineage touched turbines and post-war aviation, and it left behind artifacts and archives that historians and engineers continue to study. The last image the filmmakers capture is modest and human. Brackett's cracked piston sits under soft light in a glass case, its fractured surface magnified in a photograph nearby, with annotations by the man himself. A visiting school teacher reads aloud the small printed note attached to it. A reminder that even the strongest materials break, and that making things hold is a human endeavor. Students press faces to the glass, elbows resting on the wooden rail, and an elderly man points out grain boundaries to a grandson as if describing a map. Outside the museum, the sky is a neutral blue. The roar of those engines is now part of recorded memory rather than present sound.
This film began with a clarifying line on screen. The title is used as a narrative device. This film examines the U.S. factory whose engines made sustained strikes on Japan possible. That context matters because it keeps the story honest. The plant did not build an Interceptor for Japan. It built power for large aircraft that altered the possibilities of war. The nuance is essential. Names, Brackett, Ortiz, Kane, Wentworth, and institutions, Pratt & Whitney, Hamilton Standard, Boeing, appear as part of a network that transformed metallurgy, production, and aerial capability. The human beings who labored in those places carried pride and doubt in equal measure. If there is a lesson in this story, it is not a tidy moral, but a complex injunction. To celebrate human ingenuity without ignoring its consequences, to preserve the memory of labor, and to teach the humility that comes with power. Standing beside that glass case, one can reflect on the stubbornness required to make an engine work, and on the responsibility that comes with tools that expand reach and capacity. We leave the forge's glow behind and carry its lessons forward. The machines that once demanded all of them have been retired, but the methods, the ethics, and the craftsmanship persist in industries that shape our world today. In the pockets of archived photographs, in Brackett's annotated notes, in Ortiz's quiet mentorship, we have the story of how people learned to make the impossible routine, and how they learned to live with what the routine made possible. If this film has made you want to read more, to walk a museum floor, or to think differently about the people behind machines, consider visiting the links in the description for archival sources and museum collections. There you will find oral histories and preserved artifacts that extend what you've watched here. And if you found this deep dive meaningful, subscribe to learn more stories of machines, the hands that made them, and the consequences they carried.